Hello guys, how are you doing? So by now you've already studied about Newton's first law of motion as well as the concept of momentum, and I'm sure you have understood both these concepts very well. So today in this video we are studying about Newton's second law of motion. Now it turns out that although Newton's first law of motion defines force qualitatively, Newton's second law of motion actually defines force quantitatively. What do I mean by that? Well, you see, Newton's first law helps us understand the nature of force or the quality of force, but in no way does it tell us how we can measure it or how we can quantify it. And this is where Newton's second law comes to the rescue. Now, as I told you before, Newton's second law uses the concept of linear momentum to define force. So, let's continue our journey through the world of dynamics, guys, and talk about Newton's second law of motion today. So without sparing a second, let's begin. So, as you are already aware, force is a vector quantity, which means force has both a magnitude and a direction. Now, according to Newton's second law, the magnitude of net force acting on any object is directly proportional to the change of its momentum with respect to time. And the direction of that force is same as the direction of the change of object's momentum. Now I know that's a lot of words to take in the first go, so let me break it down and go step by step. So let's consider a simple situation where a block of mass m kilograms is initially traveling at a velocity u meters per second, let's say in the right direction. Now at time t is equal to t1 seconds, imagine that a force F begins acting on the block in the same direction of its motion. Now, due to the action of this force, the velocity of the block would certainly increase, right? Yes. So let's say at time t equal to t2 seconds, the velocity of the block becomes v meters per second. So this is the final velocity of the block, and we stopped the stopwatch at t equal to t2 seconds. Now I know I'm using a lot of variables over here, which might be difficult to relate to for some of you, but bear with me, because all of this would reduce into a simple, beautiful equation. But in any case, tell me guys, what is the change of momentum of our object over here between t1 and t2 timestamps? Well, you see, it's nothing but final momentum minus initial momentum. Now, final momentum is the momentum of the block at time t2 seconds, and the initial momentum is the momentum of the block at time t1 seconds. So, assuming my sign convention to be right side positive and left side negative, my final momentum comes out to be plus mv, and my initial momentum comes out to be plus mu. You can already verify it from the diagram. So this value ultimately becomes m times v minus u. Now pay attention that I've already included directions into the value of change of momentum, because I've already considered their respective signs. Now Newton's second law says that force on this block is directly proportional to the change of its momentum with respect to time. So mathematically I can write this as F is proportional to m times v minus u, which is the change of block's momentum, divided by t2 minus t1. Now why t2 minus t1? Well, you see, because the block's momentum changes from mu to mv between t1 and t2 seconds. So the time taken for the change of momentum is simply t2 minus t1. Now, to change this proportionality expression into an equation, I'll multiply a constant k on the right hand side and obtain an equation which is F is equal to Km times V minus U divided by T2 minus T1. Now pay attention to this term over here, V minus U divided by T2 minus T1. Does this remind you of something? Well, you see, in the chapter of motion, we studied that this is actually an expression for acceleration. Yes, acceleration is simply the rate of change of velocity with respect to time. So this fraction over here shows acceleration of the block between t1 and t2 seconds. Because clearly v is the final velocity, u is the initial velocity, and t2 minus t1 is the time in which the velocity changed. So I can replace this entire fraction with a simple variable a that represents acceleration of our block. Now before I go ahead with my equation F is equal to kma, I'm gonna go back a little bit and talk about the direction of force in terms of change of momentum. So my equation is F is equal to Km times V minus U divided by T2 minus T1. Now on the right hand side, you know that I've already taken into account the direction by assigning the proper sign conventions beforehand. So On the right hand side, t2 minus t1 is always a positive number because t1 is the starting time and t2 is the stopping time. t1 can never be greater than t2 and therefore this result can never be negative. On the other hand, mass m is also always a positive number. So depending on the sign of v minus u, we'll have the sign of force as well. If v is greater than u, we'll have a positive sign. If v is less than u, we'll have a negative sign. And if v and u are equal to each other, we'll have zero value. So depending on the sign coming out of v minus u, we'll have the sign for force. So from here you can see that the sign of net force F is exactly same as the sign of our numerator over here. Now because in our case signs represent directions, we can say that the direction of change of momentum, which is represented by m times v minus u, is exactly same as the direction of our force F. Okay, so now that you are clear about this, we can go back to our wonder equation F is equal to kma. Now this is a very interesting result, guys, and based on this I can redefine Newton's second law of motion. I can say that the magnitude of net force acting on any object is directly proportional to the product of mass and acceleration of the object, and along with that the direction of force is same as the direction of the acceleration of the object. Now that's pretty neat, I'd say, but we still have a constant k left in our otherwise beautiful equation, the value of which we do not know. So what do we do about that, guys? Well, you see, scientists figured out a sneaky way to get rid of this constant k. They defined the unit of force in such a way that the value of this constant k always comes out to be 1. Are you confused? Well, let me show you. So, scientists define the unit of force Newton in this way. They say that when 1 Newton of force acts on an object of mass 1 kilogram, it produces an acceleration of 1 meter per second square. So they are essentially saying that if I put the value of force as 1 Newton, if I put the value of mass as 1 kg, and if I put the value of acceleration as 1 meter per second square, my left hand side of the equation would always be equal to the right hand side of the equation. This is a definition given by them. Now, to be able to satisfy this equation, the value of k must be 1. Because any other value of k won't do, it will violate the equation. So like this, scientists define the value of constant k as 1 and our equation gets modified to an even simpler form, which is F is equal to ma, or force is equal to mass times acceleration. Great, guys! Now let's talk about some real life examples where Newton's second law applies. So here I have a situation. A motorcycle of mass 200 kilograms, a car of mass 1500 kilograms, and a truck of mass 6000 kilograms are all traveling at a velocity 72 kilometers per hour in the same direction. If all these three vehicles come to a complete stop in 5 seconds, which vehicle takes the most amount of force to do so? Now our common sense tells us it must be the truck. But let's go ahead and verify it. Now because the SI unit of velocity is meters per second, we need to convert the initial velocities into that unit. Now that comes out to be 20 meters per second for all the three vehicles. The method is to multiply 72 with 1000 divided by 3600. You already know it. So the initial velocity for all the three vehicles comes out to be 20 meters per second. The final velocity for all the three vehicles comes out to be 0 meters per second. And the time taken for this change of velocity is 5 seconds. Now the force acting on an object can be simply written as change of object's momentum divided by time. Now remember, the value of k is 1, so we don't need to mention that over here in this equation. Now what is the change of momentum in case of a motorcycle? It's nothing but 0 minus 200 times 20 divided by 5. 0 is the final momentum, 200 times 20 is the initial momentum. Now this value comes out to be minus 800 newtons. The minus or the negative sign represents the left direction over here. Similarly, the force on the car can be written as F is equal to 0 minus 1500 times 20 divided by 5. 0 is the final momentum, 1500 times 20 is the initial momentum of the car. Now the answer to this expression comes out to be minus 6000 newtons, where the negative sign once again shows the left direction. And finally, the force on the truck can be written as 0 minus 6000 times 20 divided by 5. 0 once again is the final momentum and 6000 times 20 is the initial momentum of the truck. The answer to this, guys, comes out to be minus 24,000 newtons, where negative sign shows the left direction. So clearly the largest stopping force is required for the truck, which is 24,000 newtons. Now let's take one more example before we end this video. So over here the problem says that a block of mass 5 kilograms traveling at a velocity 4 meters per second towards the right direction comes to a complete stop under the influence of a constant force in 6 seconds. Now given this information, you are supposed to calculate the magnitude and the direction of the force. So we should begin solving this problem by assigning an appropriate sign convention first. So let's assume that right side over here is positive direction and left side over here is negative direction. Now we can find the value of acceleration using the formula acceleration is equal to final velocity minus initial velocity divided by total time. Now in this case that comes out to be 0 minus 4 divided by 6. Now that is equal to minus 2 by 3 meters per second square. The negative sign of the acceleration tells us that the acceleration acted in the opposite direction of velocity. Now the value of force is pretty easy to calculate once we got the value of acceleration, because force is nothing but mass times acceleration. Now once we put the value of m and a over here, we get the expression as 5 times minus 2 by 3 or minus 10 by 3 newtons of force. So over here we can say that the magnitude of force was 10 by 3 newtons and its direction was left. And with that, guys, let's end our video today. I hope you had a good time learning about Newton's second law of motion. In the next video, we'll talk about Newton's third law of motion. For now, let's summarize whatever we have learned so far. According to Newton's second law, the magnitude of net force acting on any object is directly proportional to the change of its momentum with respect to time. The direction of force is same as the direction of the change of object's momentum. Newton's second law in terms of momentum can be mathematically expressed as F is equal to P2 minus P1 divided by T2 minus T1. F is the net force acting on the object, P2 is the final momentum of the object, T1 is the initial momentum of the object, T2 is the ending time, and T1 is the starting time. Newton's second law can also be expressed in an alternative way. We can say that the net force acting on any object is directly proportional to the product of the mass and the acceleration of the object. The direction of the net force is same as the direction of the acceleration of the object. Mathematically, Newton's second law in terms of mass and acceleration can be written as F is equal to ma, where F is the net force acting on the object, m is the mass of the object, and a is the acceleration experienced by the object.